Welcome to this pre-class video on amino acids. Well, what are amino acids? Well, they are the building block of proteins, which is something we're going to spend a lot of time talking about in class. Let's draw the structure of a kind of a generic amino acid. And you may say, well, where does the name come from? Well, it's fairly self-explanatory when we draw one out. This is a carboxylic acid. This is what we're going to call the alpha carboxyl group. So it's an amino acid. We know where the acid part comes from because part of the structure is always a carboxylic acid. Well, this is an amine, and in fact this is what we call an amino group. And in fact we're going to call it the alpha amino group. So now you know where the term or the name amino acid comes from. Each amino acid has an amino group, which is from an amine and a carboxylic acid group. Now, where does the alpha come in? Well, this is called the alpha carbon. This carbon here in the middle. This is called the, again, it didn't shock you, I hope, the alpha hydrogen. And probably the most important part of the amino acid is what varies in all of them. This is what, for the most part, this is what make amino acids unique from one another. This is what we call the side chain. And we'll talk certainly more about that in class and here in a few minutes. Well, what we know is that amino acids, actually, when you put them in water at about pH 7, which is when we typically find them in biological systems, they actually have a different what we call ionization form. We know acids can act like acids, amino groups are bases. So in water at pH 7 they're actually going to have this form. Like that. And again, it depends on what the R group is, but let's just focus on the the alpha amino and the alpha carboxyl group. This is at pH equals 7. Now, at the end of this video, we're going to say, well, what happens if the pH is not 7 and it's something different? Can we predict what the major form of an amino acid will be in water? Well, we can. Okay? For what I want to do now, though, is focus a little bit on the side chains, because there are 20 amino acid side chains that can be used to make proteins. In our cells there are many more amino acids, but most of them can't be used to make proteins. There's this very specific 20. And hey, good news is I'm going to give you the structure of these amino acids. So if that doesn't warrant a smiley face, I'm not sure what does. But the issue is, once I give you the structure, do you know how to use the structure to answer the question? So let's focus a little bit more on side chain classifications. In class, we'll go over the different classifications of side chains, but let me just give you one for now. Let's talk about the amino acid valine. Every amino acid has a 3-letter code and a 1-letter code, and I'm going to give you that as well. Okay? Valine, its 3-letter abbreviation is VAL, Val, and its 1-letter abbreviation is just V. And sometimes when I only want to consider the side chain, I would write it like VAL and then draw the side chain, because I don't care about the rest of the amino acid if I just want to focus on the side chain, and sometimes that will be the case. So I'm drawing you the side chain of valine. And it's just an isopropyl group that we've used before. And even more importantly, it's just a general hydrocarbon. It's just made out of carbon and hydrogen. That makes this side chain fall into the category classification of non-polar. We know hydrocarbons are non-polar. Carbon-carbon bonds are not polar bonds. carbon-hydrogen bonds are not polar bonds. So any type of hydrocarbon molecule or a group of a molecule is considered non-polar. So that is the classification of the amino acid valine. The classification of amino acids are based upon side chain. Other questions I'll ask you is, what type of interaction can the side chain participate in? Well, hydrocarbons have no hydrogen bond donors or acceptors. So this side chain will not be participating in hydrogen bonds, but it's going to be very good in participating in what we've called before dispersion forces. Dispersion forces are the main type of force among nonpolar molecules or groups, especially hydrocarbons. So you'll be given the 20 amino acids. You'll be given the abbreviations and the structure, but you have to be able to answer some questions about these amino acids that are ultimately going to be used to make proteins. And again, we'll do more on this in class. One of the main questions I'll ask you about is, hey, if I give you an amino acid, can you calculate the net charge of that amino acid in water at a given pH? And that's going to be a very important type of calculation we do. So let me just give you an example of that. Let's just start with our old friend, maybe it's our new friend now, aspartic acid. Its abbreviation is ASP, and the one-letter abbreviation is D. That's aspartic acid. I'm going to draw the structure of aspartic acid. You'll be given the structure of aspartic acid, okay? But you got to know how to use it. When I do these types of net charge calculations, I always start with the amino acid in the all acid form. Any ionizable group that it has, I will draw in the acid form. Well, there's the alpha amino group I've put in the acid form. Here's the alpha carboxyl group I've put in the acid form. There's just H. And then the structure of aspartic acid is CH2COOH. Hey, there's another COOH group. That's another ionizable group. So I'm going to draw it in the acid form. Well, something else you'll be given is every acid, and we know this, has a pKa. Lower the pKa, the stronger the acid. So we need that information. Again, you'll be given that information in a table or in a problem. So the pKa of the alpha amino group is 9.8. The pKa of the alpha carboxyl group of aspartic acid is 2.1. And the pKa of the side chain of carboxylic acid is, let's go with 3.9. All right. Now, to determine which is the major form of these three ionizable groups, you have to compare pH and pKa. Let's say we're at, I'm just giving us a pH. Let's say we're at pH equals 8. What is the major form of this amino acid at pH 8? So what we have to do is compare pH and pKa for every ionizable group. In this case, pH is less than pKa, and we know from previous rules that that makes this group in the acid form. Well, guess what? It's already drawn in the acid form. Well, just redraw it then. So that's an easy one. Okay, let's do another comparison. Here, the pH is greater than the pKa, and every time the pH is greater than the pKa for an ionizable group, like a carboxylic acid group, then you have the base form is the major form. And so let's draw that in the base form. What's the base form of a carboxylic acid? Well, there it is, COO minus. Again, we know that. We've gone over this before. Okay? And we have a similar type situation here with the carboxylic acid in the side chain. pH, the given pH is greater than pKa. This is going to be the base form. Okay, that was base. This one is base. So I'm going to draw it now, but I'm going to redraw it in the base form. The base form of a carboxylic acid is negatively charged. We know that. You need to know that. So when it comes time to net charge, you just sum up all the charges. A plus, a negative, and a negative makes the net charge equal to -1. So what's the net charge on the amino acid aspartic the amino acid aspartic acid at pH 8? The net charge is going to be -1. And again, in these types of calculations, we consider the entire amino acid. All right, we'll practice this more in class, and I hope this video was useful.